So for S and S and S, these all get bigger, but the L value stays the same. So L is equal to 0. Is L equals 0 less than 3? Yes, 0 is less than 3. Is 0 less than 2? Yes. Is 0 less than 1? Yes. Could we have a 0 s orbital? No, because L always has to be less than n. Right? So this is just the increase in the size, but you're not changing the shape. So L is equal to 0 always represents the shape code, for an s orbital. For p orbitals, L is equal to 1 always represents that shape. So 2px, 2py, 2pz, the p-nits can occupy the axes x, y, and z. Okay, so and L equals 1 represents all of these shapes. What if I had a 3p orbital? Would that change the L value? No, it doesn't, right? What if I had a 40p orbital? Again, L is equal to 1 just for that shape. It doesn't matter how big the orbital is. What if you had an infinity p orbital? It's still L equals 1. That's my new rapper name, by the way, infinity p. All right. So, what about the d's? Okay, L is equal to 2 for any of the d's. All right, so we have these orbitals here, 3d x squared minus y squared, 3d z squared, 3d xy, 3d xz, 3d yz. These last three represent the orbitals in those planes, the xy plane, the xz plane, the yz plane. The first orbital here have the lobes of the d orbitals actually on the axis, not in between the axes. So you notice how the lobe here is on the x-axis, whereas the lobes here, the axis comes out from between the lobes. Right, so you see that difference. Okay, and we have 3dz squared. This is on the z-axis. This wave function was determined from Cartesian coordinates instead of the others, which are solved differently, so it looks a little different. It's basically a peanut with a donut going around it. Okay, so L is equal to 2 for all of those. What if I had an infinity d orbital? Would the L change? It wouldn't, right? So you have to remember that the L values tell you, it's a code for telling you what is the orbital going to look like. What is this volume that the electron occupies? What is that going to look like? Okay, so just to do a couple of these. So we can. This is in your problem solving too, so we'll only do a couple. Is a 2s orbital allowed or invalid?
Allowed.
It's allowed, right? Okay, what about a 2d orbital? Is that allowed or invalid? So remember, this is the n value here. Okay. So 2s was allowed. The L value is L equals 0. And that's less than n equals 2 in this case. So that's allowed. What about a 2d? Is that allowed? Okay, so if n equals 2, and we know that for any d orbital, what is the L value for any d orbital? L is equal to 2. So is 2 less than 2? And the answer is no, so it fails. All right, it's invalid. Okay, L equals 2 is not equal to, or not less than, n equals 2. Okay, what about, let's see, what about a 3f orbital? Is that invalid or allowed? What is my L value for any f orbital? L is equal to 3 for any f orbital. So is this less than n in this case? What is n? 3, right? So is it allowed? No, it's not. All right, so this is invalid. And of course, hey, you got to do infinity p, right? Is infinity p allowed? What is the L value for any p orbital? 1. Is 1 less than n equals infinity? It is, right. So this is actually the allowed. Questions? Am I making any sense here? For at least for the last 5 seconds, maybe I'm making all the sense. Okay. Yes. Fine.
What about numbers that are higher than 3 on the orbitals? How do you determine?
What about numbers that are higher than?
Like, you know, it's like 3 is F orbital, F orbital equals 3. What about 4 orbitals? How do you determine that? Because you have 10 and 50 left there.
So you're asking if the 4F orbital would be valid?
Like, yeah, how would I determine, like, what yeah, because I know F equals.
Yeah, so all we're doing is this number that's in front, that's the quantum number n. And the rule has to be that the L value for that shape has to be less than n. So 4F is this valid, right? L is still equal to 3 for any F orbital. Is it less than n equals 4? And the answer is yes. So 4F is valid.
So the values for L only go from 0 to 3.
L can only be as high as n minus 1.
So you said memorize that table.
Yeah, memorize the numbers. Right. So if you see 4F, 2 numbers should come to mind. N and then L. Alright, but instead of saying L equals 3, now we're saying, okay, if you see a letter, you should know it's L equals 3. Right, so by looking at the letter, you should know what that L value is. Okay, and by knowing what that L value is, you can compare it to the quantum number n that's in front of that letter and determine if it's valid or invalid. Cool? All right. So what quantum rule is applied here? The rule is n must be at least, or the rule is that L must be less than n. Right, that's the rule. So those are the first 2 quantum numbers. Okay, there's a third one. We call that the magnetic quantum number, called m sub L. Okay, and the rule for m sub L is that it can take on values of negative L to plus L. And what negative L to plus L represents are the different orientations that an orbital can take around the nucleus of the atom. So for an L equals 1, for any p orbital, I showed you 3 pictures of a p orbital just a minute ago. How many different orientations for a p orbital can I have? I can have 3. Let's try to relate this a little bit to maybe something you've seen from Chem 107. I think this will really help. Okay. Tell me if you remember these diagrams. You remember these? So there's 1s, 2s, 2p, 3s, 3p. Okay, so do you remember those? All right. Now I'm going to relate that to that. How about that? All right. So for a p orbital, m sub L can be -1, 0, or 1. It can be -1 to +1. Right. The L value for any p orbital is 1. -1, 0, and +1 is negative L, 0, and plus L. Okay. Let's draw these numbers here. There's the 3 orientations. for a L equals 2, for a d orbital, you can have -2 to +2, and all the numbers in between. So if I look at a 3D array here, I have -2, -1, 0, +1, +2. So in Chem 107, we taught you, okay, you've got 3p orbitals in this 2p set. Do you remember the terms shell, subshell, and orbital? Do you remember those terms at all? You might not remember, okay, which we'll review that right now too. But what these bars represent are the different orbitals within that block of the periodic table. Okay. Now, what is the L value for S? It's L equals 0, right? So this can only be 0. And this can only be 0. Because a sphere can only take on one orientation around a nucleus, right? It just encompasses all the angles around the nucleus, right? Whereas the 2p, you can have you can have 2px, 2py, and 2pz up here. Right? But for S's, there is no x, y, and z. It's just a sphere around the whole nucleus. In this case, I would have the 3px, 3py, oops, and 3pz. Again, for the 4s, I only have one orientation. All right, so what would my all right, so these are m sub L values, all right? For the 3D, what would I have? I'd have 3D x squared minus y squared. I'm running out of room here. This would be a 3D z squared. This might be the 3D xz. 3D xy, 3D yz, right? So those 5 different orientations for the D's, okay, are shown in these 5 bars, okay? And each bar has its own m sub L value that represents the orientation of that shape. So when it comes to the volume that electrons occupy, we have the size of the volume, we have the shape of that volume, and we have the orientation of that volume around the nucleus. And so these quantum numbers represent that. I guess she didn't want to learn about quantum physics. All right. Questions? Any questions? Okay. Hopefully if I keep going, this will connect more dots. So again, what does the m sub L quantum number represent? It represents the orientation. So just run this in your mind. N is shape. I'm sorry, N is size. L is shape. M sub L is orientation of the volumes that electrons occupy. Okay. Is it an exact volume? No. It's the most probable volume. So the uncertainty principle tells us we cannot locate the electron exactly somewhere away from the nucleus, but we can approximate a volume. And Schrodinger developed this equation to solve for that volume. Okay? And that's what's going on.
So any probability of the volume of the electron?
Mm-hmm. Right, so what the orbitals represent is they represent the most probable area around the nucleus where you could possibly find an electron. Okay, remember my Superman analogy from last time? It's like Superman flies around planet Earth so fast that there's no way that you could ever infiltrate to planet Earth without being hit by Superman. The electrons are occupying all locations around the nucleus within a given volume, or no locations around the nucleus at any given time. It's like being able to transport and being in two different places at the same time. Or it's like being nowhere at the same time. If you ever seen the movie Total Recall, there's a scene with Arnold Schwarzenegger where he creates a hologram of himself. So Arnold is over here, but he's also over there at the same time. That's what electrons do. Or at least it's according to the model. Really weird stuff, right? And it's hard to wrap your brain around it, okay? But when you take all those holograms together, you create a series of most probable locations of where the electron is going to reside. And if you can solve for at least the most probable set of locations of where the electron is going to reside, you can approximate the energy of the electron by doing that. Okay, so that's the big picture of this whole thing. So yeah, again, here are the p orbitals, 3 possible orientations. Here are the d orbitals, 5 possible orientations. And again, relating it to what you may have seen in Chem 107, you see the different bars with the orientation numbers I wrote up there, the m sub L values. Here are the d orbitals. So you might remember that a d set looks like this. Do you remember how many bars go in an F7, right? By the way, with the periodic table, how many elements do you have in the bottom 2 rows of the periodic table? You should count 14. Okay, 14 representing 7 bars, and each bar holds 2 electrons. So that's 14 total electrons in that subset. So these 7 bars represent the m sub L values of -3, -2, -1, 0, 1, 2, and 3. Now I will tell you something else. Does it have to be -3, -2, -1 in this order? And the answer is no. Okay, these are just the possible numbers. I could have written 0, 1, 2, 3, and then -1, -2, -3 in that order. Okay, it doesn't matter which number goes, it's just the possible orientations. Okay. So the F orbitals have their own kind of deal here. They look like flowers. F is for flower. At least for 4 in there. I might ask you to draw these, just kidding. I'm just kidding. I can't even draw the F's for sure. Okay, so let's do a sample problem. How many 2p orbitals are there in an atom? How many 2p orbitals are there in any atom? It doesn't matter what the atom is. How many 2p orbitals? How many do I have? 3, right? How many 3p orbitals do I have? 3. How many infinity p orbitals do I have in any atom? 3. It's always going to be only 3 because all the p subsets only have 3 orientations to them. So again, try to relate it back to what you've seen from Chem 107. You've seen those orbital diagrams before. Those bars represent the different orientations of those orbitals in that subset. The last quantum number, we call that m sub s, okay, and that represents the orbital spin quantum number. Okay, and the m sub s values can take on values of +1/2 and -1/2. So imagine if an electron, which isn't really a particle, it's a standing wave encompassing the nucleus. But imagine, well, not imagine, but we also do know that electrons behave as particles. We know they have a mass, okay? So think of this particle traveling in this wave, but it also could be maybe sort of kind of spinning in place at the same time while it's orbiting the nucleus, okay, or encompassing the nucleus. Okay, so you've got this particle, it's transporting like Star Trek here, there, everywhere, but at the same time it's also spinning when it's doing that. Yeah, it gets crazy, right? And, I mean, this is just how I'm trying to make sense of it in my own mind. I'm almost thinking out loud to you. Okay, this is how I'm thinking through it. Okay, you might remember if you've ever taken physics that when a particle that has a charge rotates in clockwise directions, it creates a magnetic field pointing down, or if it goes counterclockwise, it creates a magnetic field pointing up, okay, perpendicular. perpendicular to the plane of the spinning. Do you remember, anyone hear about that? No. If you've had physics, if you take physics part 2, you'll hear about that. It's has to do with the law of induction. So when electrons spin, they create magnetic fields, okay, and that's why they call this the spin quantum number. And so you might remember from your Chem 107 that when you fill in this diagram, you get arrows. Remember? So for a 1s, I can do spin up or spin down. Okay, and so this would represent plus 1/2 and negative 1/2. This also would represent plus 1/2 and negative 1/2. If I had a completely filled 2-piece subset here, I would have plus 1/2, negative 1/2, and then repeat this for every single orbital. So every orbital that's filled has a plus 1/2, minus 1/2 spin quantum number assignment to it. Okay. So let's break it down. 1 represents which quantum number? N. S represents which quantum number? L. And there's a number assigned to that shape. The bar is represented by the M sub L number. So you've got 3 things here. N, L, and then the bar is M sub L. And then the arrow up and the arrow down is plus or minus 1/2. So you've seen this before in Chem 107, but now we're assigning quantum numbers to the whole thing. Okay? It's another level of depth. So what I would do if you want to understand this is, write out these orbital diagrams, things that you're familiar with, and just recite to yourself, and try to assign the quantum numbers to this. Okay? So here's the summary of these rules. So n is equal to 1, 2, 3, 4 on to infinity. It represents the distance of the orbital from the nucleus, the average distance. The L value is equal to 0, 1, 2, or 3. It must be less than n. That's the only rule for L. That represents the type of orbital. Okay, I would cross out the word type and replace it with the word shape. Okay, just to reinforce it. M sub L tells you the orientation of that shape, and then M sub S tells you the spin of the electron that resides in that orbital. How many electrons can reside in the orbital? 2. I can only put 2 arrows in each bar. Right? Okay. How many orbitals can I put in a infinity p orbital? How many electrons can I put in there? I can put a total of 6 in that subset, but for any given infinity p orbital, I can still only put 2. I could have infinity px, infinity py, or infinity pz, but it's still only 2 electrons to a orbital. Right, Yoshi? Don't fall asleep on me. Yes.
Okay, so I understand everything except for where's that 2 qubits? What are the?
Oh, the XYZ, that just represents the peanut on the x-axis, or the peanut on the y, or the peanut on the z-axis.
Okay, so where they're
oriented.
placed.
Yeah. So like the -1, 0, and 1 are numbers representing that x, y, and z possibility.
Oh.
Right. Again, the numbers just represent the orientation around the nucleus. Mm. Yes.
M of L, it's just orientation.
It's just orientation. Right. The L is the shape. The M sub L is the orientation of that shape. All together.
So, I mean, like, I guess you consider the location where it's at on the axis, physically.
Yeah.
Excuse me, is that slide that we're on right now, is that what you went over like maybe 5 minutes ago when you kind of summed up all of the like n equals this and this?
Right, right. I was just going through each one individually, and then this just summarizes it all.
Got it, okay.
Right. So you're not gonna get, I mean, you're gonna get this, but it'll take, like all material, it takes a little bit of time to percolate and connect. So keep asking me questions, keep probing my understanding, because it'll help it'll help me say it maybe in a way that helps you understand. So this gets me to shells, subshells, and orbitals. It sounds like a movie, like planes, trains, and automobiles, but this is just shells, subshells, and orbitals. Okay, there was a movie called Planes, Trains, and Automobiles, right? Okay, I never saw it, but I need to. Or not, I don't know, I don't know if it's a good movie. So shells, subshells, and orbitals. So what a shell is it's basically a row in the periodic table. So let me highlight a shell. So boxing this, 1s, that's a shell. Okay, we also have the n equals 2 shell, or in other words, the n equals 2 row. We also have the n equals 3 shell. So the periodic table skips or jumps to the 4s and then to the 3d. Okay, that's just the way. We'll talk about why that is later. But so the n equals 3 shell is the 3d, the 3p, and the 3s. Okay, and then the 4s is part of another shell that includes 4p, 4d, and even 4f. Okay, so these are called shells. And they are basically representing rows in the periodic table. A subshell is a set of orbitals within a row. We call it a subshell or sublevel. So the 1s shell is also a sublevel by itself. Okay, the 2s is a sublevel or subshell within the larger n equals 2 shell. Okay, the 2p sublevel is also a subshell. All right. Here's the 3s subshell, the 3p subshell, and the 3d subshell. So shells are like the big, category. They're the most broad category of orbitals. Okay, so a shell is just a row in the periodic table. A subshell, as you can see, it's broken up into sp, and then for n equals 3 shell, you've got the 3d in there as well. Oops, this is n equals 3 shell.